You're gonna have to go around your block and tell everybody.
Alright, what did we look at yesterday?
Okay, we found
y-intercepts and zeros using a graph and also using our calculator. Today we're going to start off doing the same thing, except we're going to find y-intercepts and zeros, and we're going to do it algebraically. So that means without a graph, just by looking at the function. Then we're going to determine symmetry of a relation. And then we will determine if a function is even or odd. So those are the three things we're looking at today. So we're going to start with finding y-intercepts and zeros of a function algebraically. We're going to look at the same examples we looked at yesterday to begin with, but this time we're going to find all of our answers algebraically. Okay, and then we'll verify with what we did yesterday. So I have the function 2x cubed minus x squared minus 3x, and I want to find the y-intercepts, and I want to find the zeros. So what do I do if I want to find y-intercepts algebraically? What do you got?
Set x equals 0.
Nope.
No.
Alright, you may be thinking the right thing, but the way you said it is incorrect. If you're going to find y-intercepts, you plug 0 in for x. You substitute 0 for x. See? So on this case right here, if I plug in 0 for all of my x's, what value am I going to end up with?
0.
0. So that means my y-intercept is 0. Does the graph verify that answer?
Yes.
Yes, it does. So to find y-intercepts, all I have to do is plug 0 in for x and solve for f of x or y or whatever the function is called. So in this case, if I plug in 0, I'm going to get 0. So my y-intercept is 0. Now, what do I do if I want to find zeros? I have to do something else. But yes, I will solve for x, but I have to do something else.
Set the formula equal to 0.
I have to plug 0 in for f of x or y, whatever's over here on the left side. So to find zeros, you put 0 in right there. Whoops, that's not good. Alright, so we're going to set 0 equal to my function, so 2x cubed minus x squared minus 3x. And we're going to solve that for x. When I solve it for x, that will give me the zeros. So, what's that? Alright, first thing, number one rule of factoring is see what you can take out. So we want to start by taking out an x. So I start by taking out an x. Okay, what is that 2x squared minus x minus 3? What's the name of that thing? More specifically on polynomial. Trinomial. What do we do with trinomials? Into two binomials. Good. Okay. X minus 3. Nope. Actually, it's 2x minus 1, and is that right? No. That's not right either. That's what it should be. Okay, and after we do this problem, I'll come back and talk about a factoring approach. How many of you had Ms. Yarborough? How many of you remember her approach to factoring trinomials? When there's a number in front of the x squared. Okay? Yes, well, the one where you take the slide divide is what she calls it, yes. Okay? So we'll finish this problem and then we'll come back and I'll show you how to factor using that method. So if I factor, this is what I end up with. What do I want to do at this point? What do we always do after we factor? Very good. Set them all equal to 0. So this one's done. This one gives me 3 halves, and this one gives me -1. So what did we find there with 0, 3 halves, and -1? More specifically, what are we trying to find? zeros. So I've got my zeros. Okay, and does that match the graph?
Yep.
-1, 0, 3 halves. So it does match the graph. So again, I want my answer to look like this. That's how I want you to give me the answer. I have a y-intercept at y equals 0. I have zeros at x equals 0, 3 halves, and -1. Now let's come back, and I'm going to show you that slide divide real quick as a refresher. All right, I had 2x squared minus x minus 3 is what I wanted to do. So slide divide is I take the first number times the last number. So I get x squared minus x minus 6. Then I factor this. It should be pretty easy now that there's no number in front of the x squared. Okay, so how do I read this? How do I want you to initially read it? What we talked about the other day.
What multiplies to this that adds up to this?
All right, here's how I want you to read it. I want factors of 6 subtracted to get 1. That's how I want you to initially read it. Is that what you were saying?
Yes, but not the same language.
All right. I like my language. Factors of 6 subtracted to get 1. So what are factors of 6 I can subtract to get 1? 3 and 2. So the first thing I want you to do is get the numbers. Once we get the numbers, then we come back and we see that this sign tells me to do what? Or tells me what? Not yet. What does this one tell me? It tells me my signs are different, and this one tells me which one the bigger one is. So I get that. Okay, and what was the second part of the name of this type of factor? Divide. So I have to divide by what I multiplied by. So I divide by 2 and divide by 2. So that gives me x plus 1. What happens if it doesn't divide? And you kick that over and you get 2x minus 3. Okay? It is a foolproof way of factoring if you're patient enough to do it. You can factor every time and get it right every time if you're patient enough to do it. Very easy. So again, I did 2 times the 3, gave me 6. I factored that. I divide both numbers by what I multiplied by. If it doesn't reduce all the way, then I kick the number over. There it is. Next one. All right, f of x equals the square root of x plus 3. So the first thing we want to take care of is the y-intercepts. Remind me again, Megan, how we find the y-intercept. Plug in 0 for the x. So if I plug in 0 for x, what do I get? 3. So my y-intercept is 3. So y-intercept at y equals 3. Very good. Okay, Kendrick, what do we do to find zeros?
Sorry, I just lost it.
Bailey, what do we do to find zeros?
You set the formula equals 0.
Alright, so I plug 0 in for f of x, and now I want to solve. Okay, Kurt, how do I solve that? Sure you do. Give me some.
Subtract 3.
Subtract 3. And when I subtract 3, we should see that we run into an issue. Who can explain the issue we run into here? What does that mean? You got to give me more than that. Who can explain what my issue is there?
It's not a square.
Matthew?
Yeah, you can't really square root it because it's not going to be the same number. One has to be negative while the other one's positive to be able to get a negative.
All right, you're dancing around it. You're close. Okay, the problem is whenever I take an even root of a number, what will I always get? I will always get a positive or 0. So an even radical can never equal a negative number, because anytime I take the root of a number, the even root of a number, it is always positive or 0. So this right here cannot happen, and since that can't happen, what does that mean?
No zero.
There are no zeros. And does my graph verify that?
Yeah.
Yes. Okay, an even radical cannot be equal to a negative number. Keep that in your mind. Okay, that will come up later in the year as well. An even radical cannot equal a negative number. All right, one more y-intercept and 0 before we get into the symmetry. All right, Bree, I want to find the y-intercept, so what do I do to find the y-intercept? Say it again.
Substitute x 0.
Substitute x with 0. When I do that, what do I get for my y-intercept? I get -2. Good. Okay, Reagan, what do I do to find zeros?
You have to set the column equal to 0.
Very good. So 0 equals 6x squared minus x minus 2. All right, Kathleen, what do I need to do to that?
Factor it out.
Factor it out. Let's try that slide and divide again. So what do I want to do? All right, 6 times -2. I get x squared minus x minus 12. Now, I'd like for this to be read the way I like to read it. So, Lauren, how do we read this? How do I read this? What we talked about just a few minutes ago.
You have to get the factor of 12 and have it minus or have it 1.
Okay, you're missing one word in there. I want factors of 12 subtracted to give me 1. That's what I want initially. So what are factors of 12? I can subtract to give 1. 3 and 4. Okay, then the second time I read it, AJ, how do I want to read it?
The negative version 12 means that the signs, and now the biggest number. So
Excellent. That's exactly how I want it read. Nice job. All right, what's next? Carson, what do I do next?
Which is that the factors equal to 0.
I got to do one more thing before I do that. What do I do?
You divide them.
I got to divide by what I multiplied by, so I have to divide by 6. That's the part we always. That's the problem with slide and divide is we always forget that step. Okay? Don't forget that step. So this reduces to what? 1/2, and this reduces to 2/3. So I kick the numbers over. I get 2x plus 1, and I get 3x minus 2. Now, as Carson said, I can set those equal to 0. And we get x equals -1/2, and that one's going to give me 2/3. So my answer would be zeros at x equals -1/2, 2/3. I think we got the -1/2 correct yesterday, but the 2/3, I think we were slightly off. What were we saying yesterday? Yeah, I thought we said like 0.7 or 3/4 or something like that. So we were close, but not exact. Okay, somebody remind me again what happens if I plug either one of these back into my function? I should end up with 0 very good. All right, so that is finding y-intercepts and zeros. So, Christian, what do I do to find y-intercepts?
Find y-intercepts, plug in 0 for the x value.
Plug in 0 for x. If I want to find zeros, Kendrick, what do I do to find zeros?
Set the function equal to 0.
Set the function equal to 0 and solve. Excellent. All right, now we're on to symmetry. All right, there are 3 types of symmetry. What 3 types of symmetry do we have? You said you knew it, so I'm going to let you answer. you say?
What did you say?
I said there are 3 types of symmetry. What 3 types of symmetry? What did you say? Line of symmetry. No. Kathleen, what's one of them?
Over the x-axis.
X-axis symmetry is 1. Y-axis symmetry is 2. Origin symmetry is 3. Those are our 3 types of symmetry. So we're first just going to go look through and look at it graphically and determine symmetry graphically, and then we'll come back and do it algebraically. So on this first problem, what type of symmetry would you say? X-axis. Why would you say x-axis? Because I can fold it over the x-axis. Good. Okay, what about this next one? Y-axis and x-axis, and probably origin. So that one's probably got all 3. Okay, what about this one? This one just has origin. What about this one? Y-axis. Good. That one. That one's y-axis as well. All right, I think that's it. Now let's go back and figure that out algebraically. Let's learn how to do it algebraically. So what did we say this first one has? X-axis symmetry. What's going on with the x-axis symmetry? What's something I can see and use to help me figure it out algebraically? What'd you say? What's going on here that I can use to help me figure out if I have x-axis symmetry and use it algebraically? What do you notice? What do you got?
Instead of it being y equals x equals y squared.
All right, kind of.
X has 2 y's and they're the same numbers, we just won't call them.
There it is. Very good, Marie. You nailed it. If you notice, each x value has how many y values? 2. And what did you say about the y values? Very good. They're the same number, except they are opposite values. Okay. So, for instance, if I look at the x value right here, if I look at that x value, what 2 y values go with that x value? 2 and negative 2. Okay. So, how can I use that to test for x-axis symmetry if I don't have the graph? Say again. There's nothing wrong with being wrong. You got to be willing to be wrong. You can't gain anything unless you're willing to. All right, substitute for y. What do I want to substitute for y? Okay, if I don't have a graph. What do I want to substitute? You're on the right track. I want to substitute for y, and what is it I want to substitute?
0.
No. Next try.
3.
Would be 2.
Would it be?
Positive 2 and negative 2.
There you go. I want to substitute y values that are opposites. And what should happen if I substitute y values that are opposites? I should get the same x value. That's how you check for x-axis symmetry. So what's the easiest value, easiest y value to substitute for?
1.
1 and negative 1 is what I would recommend. So let's plug in 1 and negative 1. If I plug in negative 1, I end up with 1 minus 3, and I end up with negative 2. Okay? If I plug in, hold on, something's not right. What did I do wrong?
So instead of you get the
Alright, something's not right. Oh, I'm looking over here. Okay, I'm fine. Never mind. Forgive me. I was confusing myself. Okay, if I plug in 1, I get x equals 1 minus 3, and I also get negative 2. So I plugged in opposite y values, but what did I get as an x?
negative 2.
The same x value. So when you plug in opposite y values and get the same x value, that's how you tell if you have x-axis symmetry. So again, plug in opposite y values, get the same x value, that verifies that you have x-axis symmetry.
So it would be vice versa.
We don't care about the negative 2, we just want these two numbers We want those two to be the same. If those two end up being the same, that means you have x-axis symmetry. Yes.
So would it kind of be the same if you were saying that it was a y-axis of symmetry, but vice versa, instead of x values and y values?
You nailed it. Okay, so we'll move on to y-axis symmetry. Let's go to one that had y-axis symmetry. This one right here. All right, so for x-axis symmetry, we plugged in opposite y values to get the same x. If we're doing y-axis symmetry, what should happen? You plug in opposite x values and get the same y. So let's plug in opposite x values. And again, what number do we want to use? 1 and negative 1. So I plug in negative 1. That's going to give me 1 minus 8. And gives me negative 7. Now let's plug in 1. That also gives me 1 minus 8, which gives me... So since I got the same y value when I plugged in opposite x values, that means I have y-axis symmetry. That's what's going on there. Okay, so far, if I want x-axis symmetry, what do I plug in? Opposite y's. If I want y-axis symmetry, what do I plug in? Opposite x's. Very good. Okay, now, we said this one, what did we say about this one? We said this one had origin. What do you think we do on origin symmetry? Speak up, because you're correct this time. Put in opposites for y and x when you're doing origin. Okay? So I'm initially going to plug in 1s for both, and then I'm also going to plug in negative 1s for both. So if I plug in 1s for both, I get 1 equals negative 10. Okay? Now I want to do the same thing, except this time I want to plug in negative 1s for both. And that gives me negative 1 equals positive 10. Do I have the same thing? Yes. I do have the same thing. Can I kick this negative over there? So since that and that are the same, that means I have origin symmetry. Okay, so when you get the same thing, you have origin symmetry. Question on that? So again, one more recap. How do I test for x-axis symmetry? Plug in opposite y's. How do I get y-axis symmetry? Opposite x's. And for origin, opposite both. Okay? Very good. Questions on symmetry? All right, now let's talk about even and odd functions. Now, before I get to even and odd functions, somebody tell me why, when we were talking about symmetry, we use the word relation and not function. Okay, symmetry over the x-axis means I'm not dealing with a function. Why am I not dealing with a function if I'm symmetrical to the x-axis? Yeah, I failed the vertical line test. Okay, so that's why we used a relation. Notice now, though, when I'm talking about an even or odd, we're talking about functions. Okay, so keep that in mind. So does anybody know what an even function is? An even function is a function that is symmetrical to the y-axis. An even function is a function that has y-axis symmetry, is what an even function is. Okay, what do you think an odd function is?
X-axis.
What did we just say about x-axis, though? It can't be a function.
So it's not symmetrical.
It is symmetrical, but it's symmetrical to the origin. Okay? So an odd function is a function that is symmetrical to the origin. That's pretty easy to keep straight. O for origin, O for odd. So the O's go together. Okay? And we know x-axis isn't a function, so that means that even has to be y-axis symmetry. Okay? So on these next two problems, we want to determine whether or not we have an even, an odd function, or neither. So I have f of x equals the absolute value of x cubed. I want to know, is it even, is it odd, or neither? So let's check with even first. And we said an even function has what type of symmetry? Y-axis. And we said, how do we check for y-axis symmetry? Plug in opposite x's. Okay? So what x's do we always want to use? Very good. So if I plug in 1, what do I end up with? I end up with positive 1. If I plug in negative 1, I also end up with
So it's odd.
positive 1. So that means it is symmetrical to the y-axis, which means it is an odd or an even function.
Oh, never mind.
So that one is an even function. So an even function has y-axis symmetry. One more. Okay, f of x equals negative 2x cubed plus 5x minus 4. Okay, when I'm doing even and odd, which one do we want to check first? We want to check if it's even, and how do I check if it's even? Plug in opposite x values, and we'll plug in 1 and negative 1. So this is going to give me negative 2 and 5, which is 3, and 3 minus 4 is negative 1. So now let's plug in negative 1. Alright, this time I'm going to end up with a positive 2. This will make it negative 3, so I'm going to end up with negative 7. So what does that tell me? Not necessarily. I just know that it's not symmetrical to the y-axis, which means it's not an even function. So I know it's not even. So now we need to test and see if it's odd. And what's my test to see if it's odd? Plug in opposite x and y. So I want to plug 1 in for everything, and then I want to plug negative 1 in for everything. So 1 equals negative 2, 1 cubed plus 5 times 1 minus 4. So 1 equals, so negative 2 and 5 is 3, so I end up with that. So I plugged 1 in for everything. Now I want to go back and do what? Plug in negative 1. So I'm going to have negative 1 on the left. On the right, I've got a positive 2, a negative 5, which is negative 3. Negative 3 and negative 4 is negative 7. So is this an odd function? No. Why is it not an odd function? Because these two things right here are not the same. Those have to be the same for it to be an odd function. So what type of function is this? It is a function, but it is neither. It is neither even or odd. Okay? So when you're doing these functions, your answers can be it's an even function, it's an odd function, or it's neither. Okay? So those are your three options. All right, so let's recap today. Back to the very first one, we were finding y-intercepts and zeros algebraically. How do we find y-intercepts? Plug in 0 for the x. How do we find zeros? Set it equal to 0 and solve. Usually involves some type of factoring. Good. Okay, then we determine symmetry. There are three types of symmetry: x-axis, y-axis, and origin. How do you determine x-axis symmetry? Plug in opposite y's. How do you determine y-axis symmetry? Opposite x's and origin? Both. Then if a function's even or odd, even means it is symmetrical to the y-axis, and odd means it's symmetrical to the origin. Excellent. All right, so here's your assignment. Okay, and some of these, as you've seen, are going to be the same problems as yesterday, except yesterday we were finding them graphically. Today we're finding them algebraically. So we're doing 16 to 40 even. Do not find the 0 on 22. You guys don't know how to do that yet. We'll learn that later on in the year.